How can the fundamental laws of physics be perfectly time-symmetric, treating past and future on equal footing, yet every real process we witness, from hot coffee cooling to broken eggs, stubbornly marches in one direction? Why does your morning coffee never uncool itself? In everyday life, heat flows from hot to cold because there are far more microscopic ways for energy to spread out than to concentrate. When you pour milk into coffee, the two fluids mix swiftly, yet you never see them unmix. That's because the mixed-up state has astronomically more arrangements than the ordered one, making the reverse journey essentially impossible. Could we flip the arrow of time in a tiny lab setup? Researchers have created near-reversible tricks in isolated systems. Spin echo experiments in nuclear magnetic resonance, briefly rewind spin dephasing, and optical tweezers have reversed individual Brownian particles for a split second, but each reversal demands near-perfect isolation from the environment. Any stray bump of heat or stray photon wrecks the delicate balance and pushes entropy up again. What about a friction-free, perfect engine? Could it run backward? In theory, an ideal Carnot engine between two heat baths can approach perfect reversibility, shuttling heat back and forth without net entropy change. In reality, friction, heat leaks, and mounting imperfections ensure every cycle generates a bit of waste heat. Even superconducting magnets or vacuum-insulated pistons can't escape tiny losses that accumulate into an irreversible march. Can computers ever compute without increasing entropy? Reversible computing gates promise logic operations that, if run perfectly, dissipate almost no energy, yet fabricating hardware free of electrical resistance, stray capacitors, or thermal noise is next to impossible. Every bit flip still kicks out heat somewhere, in wires, transistors, or the very act of reading a result, keeping the overall entropy rising. Is irreversibility truly an illusion or a fundamental law? Microscopically, the equations allow reversal, reverse every velocity, or conjugate every wave function, and in principle, the system retraces its steps. But the moment any system couples to a larger environment, air molecules, photons, stray fields, that reversal pathway vanishes into chill, irreversible disorder. Why should beginners care about this paradox? Because it teaches us that laws in the lab are idealizations, while the real world teems with hidden complexity and noise. Every time we pour a drink, run an engine, or boot a computer, we witness entropy's unrelenting rise. Even though the underlying rules don't forbid an opposite outcome, practical obstacles make reversals fantasies. What's the lasting lesson of the thermodynamic reversibility illusion? That the arrow of time isn't written into the fundamental equations, but emerges from statistics, chance, and the impossibility of perfect isolation. We may glimpse fleeting reversals in tiny, controlled pockets, but in the grand tapestry of the universe, every process remains a one-way ticket down the slope of ever-increasing disorder. Although the microscopic laws of physics, Newton's equations, or the Schrödinger equation, are time-symmetric, macroscopic processes almost never reverse because they overwhelmingly favor entropy increase. The notion of perfect reversibility, where every detail of a process could be undone, fails once one recognizes the astronomically large number of microstates compatible with higher entropy. Even the smallest uncontrolled perturbation makes exact reversal vanishingly improbable. Thus, thermodynamic reversibility remains a theoretical ideal, never attained in practice. Example, spin echo experiments in nuclear magnetic resonance can partially refocus dephased spins, but they recover only a fraction of their original coherence and never fully undo the diffusion. Analogy, it is like trying to unscramble an egg. You can stir it vigorously, but you will never see the yolk. At the particle level, individual collisions and quantum transitions can run equally well forward or backward in time. When trillions of such events combine, however, their collective statistical behavior exhibits a preferred direction. Entropy almost always increases. Coarse graining over microscopic details averaging out individual trajectories yields emergent irreversibility in heat flow and diffusion. This distinction explains why fundamental reversibility does not translate into observable backwards processes. Example, a gas initially confined to one side of a container will freely expand to fill it when a partition is removed, but it never spontaneously reconcentrates. Analogy, it is like watching a video of a shattered glass reassembling itself, possible frame by frame, but never seen in real life. While each microstate evolution is allowed in both time directions, the number of microstates corresponding to high-entropy macrostates vastly exceeds those of low-entropy ones. A low-entropy configuration can evolve into an enormous manifold of high-entropy states, but the reverse path requires traversing an extraordinarily narrow subset. Mathematically, the Liouville theorem preserves phase space volume, yet statistical weights overwhelmingly favor trajectories that increase entropy. Therefore, microscopic irreversibility is a consequence of this statistical bias, not a break in fundamental laws. Example, Loschmidt's paradox highlights that reversing all particle velocities in a gas would, in principle, send it back to its origin, but any tiny deviation makes that return trajectory impossible. Analogy, it is like navigating a maze where only one path leads back to the entrance. Any wrong turn seals your fate. Entropy quantifies the logarithm of the number of microscopic arrangements consistent with a given macroscopic state. Systems naturally evolve toward macrostates with larger phase space volume because there are simply more ways to realize them. Reversing an entropy increase demands steering the system into an exponentially small subset of microstates, an impractical precision. The second law emerges from overwhelmingly probable transitions rather than an absolute prohibition on reversal. Example, mixing cream into coffee increases entropy. Spontaneously unmixing would require aligning each molecule exactly, an event with near-zero probability. Analogy, it is like pouring sand into all corners of a room, expecting it to leap back into its container defies the odds. Thermal fluctuations can momentarily produce local decreases in entropy, but these events are fleeting and vanish in the macroscopic average. Coarse graining, ignoring microscopic details, erases the memory of past microstate correlations, preventing any practical reconstruction of initial conditions. Fluctuation theorems quantify these rare events, but confirm that large-scale entropy reversals remain essentially impossible. Consequently, the arrow of time crystallizes once one abandons microscopic bookkeeping. Example, in Brownian motion, particles occasionally drift backward, but never in a way that recreates an initial distribution of positions exactly. Analogy, it is like raindrops, briefly bouncing uphill on a cobblestone path before gravity resumes its dominion. The real-world systems feature friction, viscosity, and inelastic interactions that convert organized motion into heat irreversibly. Chaotic dynamics amplify tiny deviations, making reverse trajectories diverge exponentially from their originals. Once dissipative process set in, reversing them would require capturing and reconverting that heat back into work with perfect efficiency, a thermodynamic impossibility. These nonlinear dissipative thresholds lock in irreversibility for virtually all practical purposes. Example, a pendulum in air will never return to its exact starting height due to air resistance and bearing friction dissipating energy. Analogy, it is like trying to rewind a videotape with a single damaged frame. You lose continuity and cannot restore the original sequence. Reversible computing is theoretically possible but demands zero energy dissipation per logic operation, unattainable at finite speed or scale. Biological organisms maintain local order by exporting entropy but cannot repair every molecular misstep without expending energy. Cosmologically, the universe's initial low entropy state sets the global arrow of time, making universal reversal implausible. Across domains, true reversal remains an illusion enforced by statistical and energetic limits. Example, erasing a bit of information in a digital circuit unavoidably dissipates a minimum amount of heat, as per Landauer's principle. Analogy, it is like scrubbing away graffiti. No matter how hard you clean, some residue always remains unless you add extra chemical. Laboratory protocols like spin echoes or Low-Schmidt echoes can partially invert microscopic motion, but only under exceedingly controlled, nearly isolated conditions. Scaling such techniques to macroscopic systems fails because unwanted environmental couplings destroy the delicate correlations needed for full reversal. Poincare recurrences in finite systems would return them to an initial state only after times vastly exceeding the age of the universe. Practical observation of complete reversal is therefore beyond any realistic experiment. Example, in ultra-cold atom traps, researchers have reversed certain many-body dynamics briefly, but coherence is lost almost instantly when the trap dims. Analogy, it is like trying to re-roll dice after 100 throws and expecting the exact same sequence. The odds and time required are astronomical. Advances in quantum control, error-correcting codes, and non-equilibrium thermodynamics push the boundaries of near-reversible operations but still confront fundamental dissipation. Investigations into the universe's early, low-entropy conditions may reveal why the arrow of time emerged at all. Exploring minimal dissipation limits could yield more efficient engines and computing paradigms. Ultimately, the thermodynamic reversibility illusion teaches us that while microscopic laws permit reversal, macroscopic reality overwhelmingly forbids it, a profound lesson about the nature of time itself. Example, quantum simulators aim to implement nearly dissipationless logic gates, approaching but never fully reaching thermodynamic reversal. Analogy, it is like attempting to stop a waterfall by reversing every water molecule's trajectory, a feat conceivable on paper but impossible in practice.